Hi, welcome to your lesson on radian measure and arcs, sectors, and segments of a circle. Let's begin with a circle. This is called the circumference of a circle, and this is called the diameter. When you divide the circumference by diameter in any circle, you will always get 3.14 and then more decimal places. In other words, circumference divided by diameter is pi. This happens for any circle. Let's say we had a circle here, circumference, and then the diameter, and you divided those. Again, you would get pi. How about in this sumo ring, which is also a circle? We take the circumference, we divide by the diameter, we will get pi. Circumference by diameter is always pi. Hey, surely this won't work for planet Earth. Well, it certainly will. We have a giant circle, circumference divided by diameter, we get pi again. Alright, that's a property that was discovered many thousands of years ago, and it's an important one. If we take that and rearrange it, we get circumference equals pi times d. And then d, we know the diameter is actually 2 radii, so we have circumference equals 2 pi r, one of our key formulas for circles. Let's begin there and go a little further. Let's talk about a radian. A radian is an angle that occurs in a circle when you take the length of the radius and you wrap it around the circumference of the circle. The angle that is created is called a 1 radian angle. Therefore, if we have the circumference of a circle, and we know it's 2 pi r, so we know this whole circle has a circumference of 2 pi r. If you want to find out how many of these segments make up this circle, or how many radian pieces go around one circle, you can just say, well, the whole circumference is 2 pi r, and we know this length is r, so I'm going to divide 2 pi r by this length to see how many of these lengths wrap around the circle. So 2 pi r divided by r, well, the r's cancel and we're left with 2 pi. So we just found out that 2 pi, which is a number, this is about 6.28, there are about 6.28 of these lengths around the outside of a circle. Very important to know. 2 pi radians in one circle. So there's 2 pi of these angles, 6.28 of these angles that go around in a circle to make 360. Okay, that idea can be shown right here. We have a radius, we create a circle, then we take that radius and we wrap it around a portion of the circumference like that. When one radius is wrapped around the circumference like that, we get an angle. That angle is called a 1 radian angle. Alright, now we have 2 radians, 3 radians, so we have 3 of those angles, and then there's just a little bit more we need, and that together makes 3.14 pi, so we need pi to come around halfway in a circle. Therefore, to go a full revolution in the circle, we'll need 2 pi. So there's our answer again, 2 pi radians to go around in a circle. Alright, let's take some notes. So a radian is the measure of the angle created when the arc is the length of the circle's radius. We've defined that already. 2 pi radii can wrap around the circumference of a circle. Therefore, a full rotation is 360 degrees, or 2 pi radians. So degrees is one way to measure angles, radians is another way. Therefore, how many degrees is 1 radian? Well, you can just divide 360 by 2 pi, and you can find out that 1 radian must be 57.3 degrees. Okay, that was a summary. And so that you know, Babylonians believed that there are 360 days in a year, hence they came up with 360 degrees to represent one revolution or one circle. Okay, let's move on from there to an important formula. We just learned that 2 pi radians is 360 degrees. Therefore, pi radians is 180 degrees. So, if somebody said, what's 60 degrees? How many radians is that? Well, if 180 makes 1 pi radian, and 60 is a portion of 180, then 60 must be a portion of pi radians. We can figure that out by doing 60 over 180 to figure out what portion 60 is out of 180. Multiply that by pi, and we'll get how many radians we have. 60 over 180 is 1/3. So we have 1/3 pi radians. That makes sense. If 1 pi radian is 180 degrees and 60 is 1/3 of that, we have pi over 3 radians. which is equal to 60 degrees. That brings us to important formulas for converting from degrees to radians and radians to degrees. So if we want radians, we can just take our degree number and multiply by pi by 180, and that's what's going on here. We see pi times 180, pi over 180 times 60 right here. So we can just multiply like that. If we want to convert from radians to degrees, we can just take the number of radians and multiply by 180 over pi. So remember that to get radians, we do pi times pi over 180 times the degrees, and vice versa for finding degrees. Let's try that here. So there's the two formulas again. Try to convert this angle to radians and this one to degrees. Okay, let's check our work. First one, this degree angle multiplied by pi over 180. Look at the cancellations that happen. We get 3 over 4 pi radians. Okay, the other one was 5 pi over 12 radians changing to degrees. We multiply by 180 over pi. Notice the pi's cancel. The 180 and 12 can reduce to 15. So we end up having 5 times 15 equals 75 degrees. Check your work carefully there. There's just some work with fractions you have to be able to do there. If you need more practice with this, there's a practice assignment that follows this video. Alright, let's try 3 more. It'll give you a few more chances to practice. Convert these two to radians and this one to degrees. Okay, and now check your work, see how it went. Remember, for degrees to radians, we multiply by pi over 180, so that's what's going on here. Again here, multiply by pi over 180 to get this when this is reduced, and then when changing from radians to degrees, we multiply by 180 over pi, and that reduces to this. Okay, great work. Let's talk about some circle vocabulary. This is an arc right here. This is a sector. So we're going to talk about arcs and sectors now. So sectors are like slices of a circle from the center. Arcs are pieces of the circumference, and then we also have chords and segments. Segments is just any slice like this that does not necessarily go to the middle or center. Okay, we have minor arcs, the short ones, and major arcs, the ones that are longer than 180. And we have major sectors, big slices, or minor sectors like this. Alright, so here's a minor arc, here's a major arc, and here is a semicircle, which is neither minor nor major, it's exactly halfway. Alright, so an arc, or arc length, is considered a part of the curve or circumference of the circle. So imagine a piece of the circumference. So let's look at arcs in this way. Let's say we had this looks like about halfway around the circle. So if we knew the circumference is 24, we could say the arc AB is 12. We're assuming this is halfway around the circle. Alright, how about this one? We have those 2 points, and we say the circumference is 44. How long is the arc? Well, in this case, the arc is about 1/4, so 1/4 of 44 is 11. 1/4 of the circumference. Okay, then we have an arc like this. The circumference is 40. This looks like 3/4 of the circle, so the arc must be 3/4 of 40, which is 30. Okay, let's say we had 180, and one time around the circle is 360, so we know here we have 1/2 of the way around the circle. Okay, how about here? If we have 120 here, what portion of the circle have we done? Well, that's about 1/3 of the way around the circle, and to get that 1/3, we can just do 120 over 360. Okay, remember that. So let's look at this one. What portion of the circle is that? Well, that's like 60 out of 360, which reduces to about 1/6 of the way around the circle right here. How about this one? This one we have 40 over 360, which would be 1/9, so we have 1/9 of the portion of the circumference of the circle. Alright, so using that property, if we have a circumference of 30, and we're told the angle is 180, what will be the arc length? Well, by the logic we just saw, we can say the arc length is 1/2 of the entire circumference, so 1/2 times the circumference, which is 15. How about these? Try these 3. Okay, now check your work. That one was 1/4 of 160. This one was 1/3 of 225, or 1/3 of the way around the circle. And 60 degrees is 1/6, so 1/6 of 420 equals that. This one, and check your work here. We have 240 over 360, which is 2/3 of 63. 42 is our portion if we have that arc. Okay, so this brings us to a formula. What is the general rule we can have? If we were saying that we have 1/3 of circumference here, remember what we did with the 120 over 360. So what would be a general rule using theta? The rule could be this. We always take a portion of 360, the angle over 360, times 2 pi r, which is our circumference. So what portion of the circle do we have? Times the circumference, and then we get the arc length. Okay, arc length formula, we're going to be working in radians. So we just figured out the degree arc length formula is this. What portion of 360 do we have times the circumference? Let's do the same thing in radians. And notice we're using the letter L for arc length. In radians, we have an angle that's a portion of 2 pi, because 360 degrees is 2 pi radians. So we say theta over 2 pi, and then multiply that by the circumference 2 pi r. But notice here our pi's can cancel, therefore this formula becomes, and also the 2's cancel, the formula becomes arc length equals radius times theta, where this is an angle in radians. It can only apply for an angle in radians. There's our formula for radians, arc length. Okay, now let's talk about sector. A sector is a plane figure bounded by two radii, imagine radius, radius, and an arc. So that's a sector. It is considered part of the area of a circle. Just like our arc was part of the circumference, sector area is part of the entire area. So here's an example. We have a circle, and we see that we have 1/4 of it, and we know the full area is 224, so what would be this area? Well, just like before, we can say we have 1/4 of the total, so 1/4 of that is 56. Let's try this one. Try to find the area of sector FOC. Okay, using the same logic that we used for arc length, we can say what portion of 360 do we have? Well, we have 113 out of 360, and we multiply that by not the circumference 2 pi r, but by the area of a circle, because we have a portion of the area when we're talking about sectors. So portion of the area, so multiply all those, and you are left with this, which can also reduce to this if you get rid of the pi and multiply through. So again, remember sector area is a portion of the area, whereas arc length was a portion of the circumference, so this changed here. Okay, so now our sector area formula in degrees was this, a portion of 360 times the area of a circle. But in radians, this will be this, a portion of 2 pi times pi r squared. So what cancels this time? This time you can cancel the pi and the pi, and you're left with this. So this is the area formula for a sector of a circle, given when you have an angle that is in radians. Alright, so now using the two formulas, our two radian formulas, we had a radian formula for arc length and one for sector area. How about trying this? Find the arc length here, and then find the sector area there. And you notice you're given an angle in radians here. Whenever you see that pi there, you know it's probably a radian angle. Okay, check your work. So here's arc length using the formula, reduced, and here is area using the formula we had, reduced as well, leaving the pi in there to make it precise. Check your work carefully there. These are simple, but also our first application of these two formulas, so make sure you know how to use it. Alright, let's try another one. In this case, we were given we didn't have the angle, but we knew the arc length and the radius, so we used the arc length formula and we solved backwards for the angle. So we found out the angle is this in radians because we used the radians formula. And now that we know that, we can find the area. Now that we found the angle, we put it into the area formula and find the area, which works out to this. Okay, hopefully you're able to do that. Let's try another. Try this. In this case, you were given the area, therefore use the area formula, work backwards to solve for this. And then you're also given the arc length here, work backwards to solve this. Now we can take this theta, we have a system of equations, take that, substitute it in here, and then you can solve for r. That one's a little tougher, but hopefully you figured out you can use a system of equations there. Check your work carefully, that's a good problem. This one. Okay, notice in this one you're looking for this part here. It is a segment. To do that, you need to begin with the area of the entire sector, which is here, and then find the area of this triangle using the triangle area formula we learned in the previous unit, and then you subtract those two to get your segment area. Great problem, study it carefully. Great job.